Hi and welcome to Concept Based. I'm John Hepworth and this is a Year 11 advanced topic. We are still in the working with functions section of your syllabus, and this is in the piecewise defined functions. And this question is very similar to an example that's given in the syllabus. A couple of bits of the functions changed around, so it's something that you could probably expect in the HSC in the future. All right, so what we're looking at doing is graphing the function. Now, when we're talking about graphing a piecewise function, as is often the case with mathematics, lots of things always rely on your ability of something before. You need to understand some concepts of what you did earlier so as you can do the new thing. So let's think about what do we need to know to do this. Well, first of all, we need to know how to graph x squared, x plus 1, and 2 root x. So hopefully in the Year 11 advanced course that you're in, you're able to graph almost all of the functions, if not all of them, so that when you get to this piecewise section, it's not the graphing of the functions that's the thing you have to think about. It's what I'm actually doing in relation to the part where it's piecewise. So then there's the piecewise part, which really breaks it up into 3 different graphs, and each of those graphs have their own domain. Now, in a previous video, I spoke about domain notation and how you had to be across that and how there are 3 different forms. These ones in the piecewise functions are often presented in the inequality form of the domain. So you just need to make sure that you're across how does that work in terms of doing correct domains. One thing obviously to take note of here in this piecewise function, we've got less than or equal to, less than or equal to again, and a greater than. So there are the ones where they're equal to, and there's the ones where they're not equal to. Now, in the syllabus, you are required to designate on the ends of the graph where those domains end, whether or not that is included in the graph or not included in the graph. And the way you can designate that it's included in the graph is a colored in dot. And the way that you can indicate that it's not included is an open circle. And the way that I always tell my students to try and remember this is that if you have a value, so here's the x-axis down here, if we put the x value in and it hit the function, well, it's part of the function, but if we put an x value in and it goes through the loop and doesn't hit the function, then it's not part of the function. So this one here would be not equal to, and this one here would be like greater than, not equal to, this one here greater than or equal to, or less than or equal to, because I haven't drawn the graphs on them. So you need to know that part. So closed circles and open circles, you go through the hoop if it's not equal to. Okay, so let's go about answering this question then. So what strategies should we use? Well, as I mentioned, we do need to be able to graph some things before we do this. So I'm going to make the assumption, which is always dangerous in the classroom, that you can graph them. So I'm going to give minimal explanation about how the graphs are what they are. So the first graph is x squared. So I'm just going to do a dotted x squared graph like this. Now, some people may not do the whole thing. Some people may look at the domain that it's in where it's less than -1 and just graph that part. Personally, I like to put a lot of it in and then go and firm in over the top of where I care about. So let's say we're doing -1 here and 1 here. -1 squared is 1, so that's hitting my graph at 1. That would make that accurate. Okay, so the next graph is x plus 1. Very hopeful that we are graphing x plus 1 accurately. So that goes through there. So when we're at 1, 1 plus 1 is 2. So this is the part of my graph hitting at 2. Now these little scribbles I'm putting on the graph, they're not the open circles or closed circles or anything like that. I'm just indicating. And then the last part is 2 root x. So let's think what happens at 1. We put 1 in, square root of 1 is 1, and 2 times 1 is 2. So it actually hits at the same part. When it's at 1, it's at 2. Now we need to consider what happens when we graph root x in comparison to that line x plus 1. Hopefully you realize that root x, with it being curved down, is going to always stay below that x plus 1 line. I mean, we could put a value in to check it. What about if we put 4 in? The square root of 4 is 2. 2 times 2 is 4. And then if we put 4 into the line, 4 plus 1 is 5. So the line's above the 2 root x function. So after they cross, or after they touch, then the 2 root x function goes below the function. Okay, so I've drawn my first part in. Now I'm looking at this dot here, and I know that I'm going into my x plus 1 line, and that's going to go all the way down to the 1. I missed my 1 on my axes. Okay, now I've got to take into consideration this next part, this x squared, and I can see that it's not touching. Okay, we're looking in this part here. So my x squared function is not touching this function. Here's my x squared function. So because they're not touching, I then need to go in and identify what's going on each graph, which one's included and which one's not. So if we look at this x squared function, this one has the less than or equal than part at -1, whereas the x plus 1 has just the less than. So just the less than is not included. So the x plus 1, the line, not included. So that's an open circle on the end of that one. Whereas the x squared is included. So that is a closed circle on that one. Now there's no defined size for these circles that you need to put on your graphs. Just big enough to indicate to the marker that you're demonstrating you know exactly what it is that you're doing. Now this question doesn't, and that's it for this question, right? That's the piecewise graph of this. You don't need to go and rub out your working lines. The markers know that they exist for your, helping you. As long as just the lines that you've drawn in solid are accurate, then they will go ahead and just mark that. If I'm in the HSC, I'm 100% always labeling my axes, putting arrows on them, and making sure that I'm not missing out on marks because of that. Okay, so one other thing you might be asked about is to describe where the graph is continuous. Now in your syllabus, and I'll quote from the syllabus, define informally that a function is continuous at a point if the curve can be drawn through the point without lifting the pen off the paper. So over here, they are connected, so we would definitely say it's continuous. So we could say that this function is continuous everywhere. I can't undo that box. Oh, it's the equation that's highlighted. There we go. We can say it's continuous everywhere. The only place we would say that it is not continuous or discontinuous is at this section here. We have to take our pen off when we skip the 2 functions across. So we would say that there is a point of discontinuity at x equals -1. So that's it for piecewise graphs. For anything to do with this graph, I would recommend first and foremost, just make sure your graphing of all your different graphs that are available in the advanced course are strong. And if you are strong at graphing, then you'll find that this piecewise part that is added on is quite simple and really accessible.